Welcome back to Unit 3 of our networking course based on the text by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. You recall in Unit 1 we had an overview of the entire course. Then in Unit 2 we started our examination of the application layer of the TCP/IP model. And in fact, that is the basis of the text. It is a study of networking from the viewpoint of the TCP/IP model based on 5 layers, starting at the top with the application layers, then the transport layer, network layer, data link layer, and physical layer. And last unit was on the application layer, and Unit 3 is on the transport layer. We've stepped down a notch. We did talk quite a bit, you recall, in Unit 2 about the transport layer. Remember that in the viewpoint of the service model, each layer provides a service to the layer above. And with the application being the topmost lever, the transport layer is the first of those layers that provides a service to the layer above, being the transport layer. So we did talk about the transport layer quite a bit whenever the application needed to transmit the data. It had to pass it on down to the transport layer and explain some of the issues about that with the various applications. So now let's expand on this discussion and get into our coverage of the transport layer. The transport layer is located between the application and the network layers of the TCP/IP model. It provides end-to-end communication services, meaning that it is responsible for ensuring that the applications on the sending host and the receiving host are successfully communicating. We're going to explore transport layer principles and how they are implemented in existing protocols, in particular the TCP and the UDP transport layer protocols. We start by discussing the relationship between the transport and the network layers. The network layer is like UPS or the Postal Service is to us. The post office is responsible for taking a package from us and delivering it over to the network of carriers and offices to someone else, as it is our responsibility to make certain that the package is properly labeled and bundled in a form that the post office can process. It is the transport layer that has that similar responsibility for data communications. You might say that the letter we've written and that will be read at the other end is our application layer, and the envelope, stamp, addresses, and so on are our transport layer. You might make a simplistic characterization by suggesting that the mailing of the letter is like a UDP protocol, and by adding a return receipt to our letter, we are using the TCP protocol. I believe that is simplistic. As we're going to find out, there's a lot more to the transport layer. We'll then return to principles and confront one of the most fundamental problems in computer networking: how two entities can communicate reliably over a medium that may lose or corrupt the data. We'll then explore the controlling of the transmission rate of the transport layer entities to avoid or recover from congestion within the network. We'll consider the causes and the consequences of congestion, as well as commonly used congestion control techniques. A transport layer protocol provides for logical communication between application processes running on different hosts. Logical communication means that from an application's perspective, it's as if the hosts running the processes were directly connected. In fact, the hosts may be on opposite sides of the planet, connected by numerous routers, wide range of link types, and so on. Application processes use the logical communication provided by the transport layer to send messages to each other. The application layer is no more concerned about the details of the physical infrastructure used to carry these messages than we are about which plane our letter to Europe is on or which airport it passes through on the way. The image in this slide illustrates the notion of logical communication. Transport layers are implemented in the end systems, not the network routers. On the sending side, the transport layer converts the application layer messages it receives from a sending side process into transport layer packets, known as transport layer segments in Internet terminology. You recall our earlier discussion of protocol data units, messages, segments, packets, datagrams, and frames. The PDU for the transport layer is the segment. This is done by breaking the application messages into smaller chunks and adding a transport layer header to each one of those chunks to create the transport layer segment. The transport layer then passes the segment to the network layer at the sending end system, where the segment is encapsulated within a network layer packet, or PDU, referred to as a datagram, and sent to the destination. It's important to note that network routers act only on the network layer fields of the datagram. That is, they do not examine the fields of the transport layer segment encapsulated with the datagram. In fact, all they see are a number of bits, really with no knowledge of what represents data or what represents header information from a prior layer. On the receiving end, after passing through any number of intermediate routers, the network layer extracts the transport layer segment from the datagram and passes the segment up to the transport layer. That is to say, it strips off its own network layer header and passes that bunch of bits on up. The transport layer then processes the received segment, making that data in the segment available to the receiving application. More than one transport layer protocol may be available to network applications. For example, the Internet has two protocols we talked about in the last unit, TCP and UDP. Each of these protocols provides a different set of transport layer services to the invoking application. Recall that the transport layer lies just above the network layer in the protocol stack. Whereas a transport layer protocol provides logical communication between processes on hosts at each end, a network layer protocol provides logical communication between hosts. The distinction here is subtle, but it's important. It provides logical communication between the hosts along the path from source to destination. Transport layer protocols live in the end systems. With an end system, a transport protocol moves messages from the application processes to the network layer and vice versa. But it doesn't have any say about how the messages are moved within the network core. That is, the transport layer has nothing to do with the route that packets will take as they travel along the network. Also, intermediate routers neither act on nor recognize any information that the transport layer may have added to the application messages. Those routers, part of the network layer, are only concerned with passing the packets on to their final destination. A computer network may make available multiple transport protocols, with each protocol offering a different service to applications. We've already talked about TCP and UDP. This slide shows hints of an analogy of two households to compare snail mail delivery to TCP delivery. You can read more about that in the corresponding text chapter to this unit. The services that a transport layer protocol can provide are often constrained by the service model of the underlying network layer protocol. If the network layer protocol cannot provide delay or bandwidth guarantees for transport layer segments sent between hosts, then the transport layer protocol cannot provide delay or bandwidth guarantees to the application messages sent between processes. Nevertheless, certain services can be offered by a transport protocol even when the underlying network protocol doesn't offer the corresponding service to the network layer. For example, as we'll see in this unit, a transport layer protocol can offer reliable data transfer service to an application even when the underlying network protocol is unreliable. That is, even when the network protocol loses, garbles, or duplicates packets. A transport protocol can use encryption to guarantee that the application messages are not read by intruders, even when the network layer protocol cannot guarantee the confidentiality of transport layer segments. Remember from a prior lesson that the network layer protocol takes the segment passed down from the transport layer protocol and possibly breaks it into multiple datagrams for transmission across the network. As we learned earlier, each layer protocol has its own specifications for how large a package can be. So the transport layer segment may be larger than allowed by the network layer packet. So the network layer protocol will break that message up, adding its own header information, which will include how to reassemble the messages at the other end, and then sends the packets on. If, as part of the transport layer protocol, that segment is encrypted, then the bits that the network layer protocol is separating into smaller packets are also encrypted. So even if a packet ends up in the wrong hands, all the unauthorized host would have is gibberish. Recall that the Internet, and more generally a TCP/IP network, makes two distinct transport layer protocols available to the application. One of these protocols is UDP, which stands for User Datagram Protocol. And this protocol provides an unreliable, connectionless service to the invoking application. The second of these protocols is TCP, which stands for Transmission Control Protocol. This protocol provides a reliable, connection-oriented service to the invoking application. When designing a network application, the application developer must specify one of these two protocols. The application developer selects between UDP and TCP when creating those sockets that we learned about in the last unit. To simplify terminology, when in an Internet context, we refer to the transport layer packet as a segment. We mentioned, however, that Internet literature also refers to the transport layer packet for TCP as a segment, but often refers to the packet for UDP as a datagram. But this same Internet literature also uses the term datagram for the network layer packet. So for our purposes, we're going to refer to both TCP and UDP packets as segments and reserve the term datagram for the network layer packet. The Internet's network layer protocol has a name, IP, for Internet Protocol. IP provides logical communication between hosts. The IP service model is a best effort delivery service. This means that IP makes its best effort to deliver segments between communicating hosts, but makes no guarantees. It does not guarantee segment delivery. It does not guarantee segments in any order. And it does not guarantee the integrity of the data in the segments. For these reasons, IP is said to be an unreliable service. Let's also mention here that every host has at least one network layer address called an IP address. But now that is the network layer, not the transport layer. Let's summarize the service models provided by UDP and TCP. The most fundamental responsibility of UDP and TCP is to extend IP's delivery service between two end systems to a delivery service between two processes running on the end systems. There's a pretty good distinction there. The network layer is responsible for getting packets to the end systems. The transport layer is responsible for getting packets to the particular processes running on the end system. Extending host-to-host delivery to process delivery is called transport layer multiplexing and demultiplexing. We'll discuss transport layer multiplexing and demultiplexing in the next lesson. UDP and TCP also provides integrity checking by including error detection fields in their segment headers. These two transport layer services, process-to-process data delivery and error checking, are the only two services that UDP provides. Like IP, UDP is an unreliable service and does not guarantee that the data sent by one process will arrive intact or even arrive at all to the destination process. TCP, on the other hand, offers several additional services to applications. First and foremost, it provides reliable data transfer using flow control and sequence numbers, acknowledgements, and timers, which are techniques we explore in detail in this chapter. TCP ensures that the data is delivered from sending process to receiving process correctly and in order. TCP thus converts IP's unreliable service between end systems into reliable data transport service between processes on those end systems. TCP also provides congestion control. Loosely speaking, TCP congestion control prevents any one TCP connection from swamping the links and routers between communicating hosts with an excessive amount of traffic. TCP strives to give each connection traversing a congested link an equal share of the link bandwidth. This is done by regulating the rate at which the sending sides of TCP connection can send traffic into the network. UDP traffic, on the other hand, is unregulated. An application using UDP transport can send at any rate it pleases for as long as it pleases. At some point in our discussions, we'll discuss why any application would use UDP at all. A protocol that provides reliable data transfer and congestion control is necessarily complex. We'll need several lessons to cover the principles of reliable data transfer and congestion control, and additional sections to cover the TCP protocol itself. Well, I think that is a good, thorough opening lesson for our Unit 3. So let's stop here, take care of any business that you need to take care of, study the notes that you've taken and the study guide that you have updated on this material, and when you're ready to come on back and we'll proceed to Lesson 2.